Welcome. Good morning, good afternoon, good evening. We're going to be doing some review of tangent lines. So let's review what a tangent line is and the derivative and slope and how all of those terms relate to each other. So we are given a function here, which is a curved function, a parabola, negative 2x squared plus 8x minus 2. And remember that with these curved functions, specifically parabolas, their rate of change is constantly changing. The rate of change is not constant. So if I put any points on a line, the slope at that point, the rate of change there is going to be different than the rate of change there, which is going to be different than the rate of change there, different than there, and different than there. So all of those points have different rate of changes. So we've got to be able to find what is the rate of change at any one point. Now, our old method was to, connect 2 points and find the slope, but that's going to give me the slope of a straight line, not the slope of a curve. So we have to think about this differently. And for the slope of a curve, we're not going to kind of just refer to it as slope as much as we're going to call it the instantaneous rate of change. So what I'm looking for is really the instantaneous rate of change at this point right here. So what we do is we actually find the slope of the tangent line. The slope of this tangent line is going to tell us the instantaneous rate of change of our function at this particular point. Remember that tangent lines just intersect at a specific point. So some words that I want to relate to myself are line that is tangent to would be instant rate of change. And all of this is talking about how and why we use the derivative. Okay, which we have annotated down here with that f prime symbol. That means derivative. So we've got two different things to consider here. What is f of 3? Well, that's just if I plug in x to my regular function here, that would be the y value that corresponds with it, right? Plug in the x to get the y to find a point that exists on your function. Now, if I find f prime of 3, it's not a point on my function. That's actually the derivative, right? Which tells me the slope of f of x at x equals 3. Or the instantaneous rate of change at x equals 3, which we now have as basically the slope of the tangent line. All of these things meaning the same thing. That's how I kind of go through that information in my head. So what is the slope of this tangent line? We'll just use rise over run. It's down 4 over 1. So that means that at this exact point, this curved function has a rate of change of negative 4. So that's what it looks like, and that's what we'll be kind of grounding ourselves in as we do this. Now, we have some methods for solving this without a graph. And one of those methods was the limit definition of the derivative. And I'll show you right here. This is what we did before. We took this limit definition of a derivative to find that slope and narrowed it down to basically just 1 point. By plugging in basically, x plus h and x with given that x value, factoring, right? And then plugging in 0 for our h to get 12 down here. So if I do all of this work with my limit definition of my derivative, I can find the slope, the instantaneous rate of change at that point. But what I want to talk about today is that there's a different method. That instead of using this to find my derivative, we can use, well, a shortcut called the power rule. And what we're going to get into is how do we use the power rule to take a derivative and still find that same answer, still find that slope of our tangent line, still find that instantaneous rate of change without having to do quite as much work. And so this is what we're going to ground ourselves in today, is basically finding the derivative using the power rule. So let's get into an example. We'll call this 8.05. Our power rule works like this. If given a function f of x equals x to the power of n, so basically the power rule is used for any function that has a power. That might be too broad of a generalization. We'll be using these for polynomial functions that have an exponent. Our derivative is going to be just basically moving that n down to the front, whatever that exponent is going to become the coefficient. We're going to keep the x, and then we're going to subtract 1 from whatever that exponent is. and this would be our derivative. So if we need to find the derivative of some function, let's actually see if we can use this now. If given f of x equals, let's say, x to the 4th power, then the derivative function would be, let's see, I would move that exponent down to the front. The exponent becomes the coefficient. Keep that x there, and then I'm going to subtract 1 from whatever that exponent was. So that becomes a 3. There's my derivative. Let's say I have g of x equals, I don't know, x to the 10th. To find my derivative, we can just move that 10 down to the front. That becomes the coefficient. Keep the x and then subtract 1 from that exponent. That becomes 9. This is my power rule. All right, so this is how we find the derivative. And that is going to be such an essential concept for us. Now, if you want to go into one that's maybe slightly more difficult, I'll give you one that says maybe, I don't know, 4x to the 5th power. Now, when I do the derivative of this, you'll notice that that 5 is going to come down, and we have not only a 5 out front, but we also have a 4 out front. Well, we're just going to multiply those two coefficients together. So if the 5 comes down with the 4, and then we're still going to subtract 1 there to make that a 4. So our derivative here is going to be 20x to the 4th. All right, so in your own words, here's what I would, or in my own words, here's how I would describe the power rule. First step, move exponent down. Step 2, subtract 1 from the exponent. All right, and I did that in each one of those. I brought the 4 down, and then I subtracted 1. Brought the 10 down, subtracted 1. Brought the 5 down, multiplied those two things, then subtracted 1. And why is this important, and why is this so useful, and why is this so great to have? Is because now we can actually find, let's say, the slope of the tangent line, or the instant rate of change of a function at a point. So let's find the instantaneous rate of change of f of x equals 3x to the 6th at x equals -1. So in order to actually find that instantaneous rate of change now, the first thing that I have to kind of remind myself is instantaneous rate of change is talking about the slope of the tangent line, or the derivative. So I'm going to take the derivative. Bring that 6 down. That gets multiplied with the 3. And that 6 becomes a 5. Now, we can just plug in a -1 into our derivative function. And this is replacing all of that work that we did before at that limit. And this is just going to become 18 times -1, which is -18. So there's my slope. There's my instantaneous rate of change. There's my slope of the tangent line. Found my derivative using the power rule, and then I plugged in.